Hello class! This lesson is 4.6, Elastic Potential Energy and Simple Harmonic Motion. So we're talking about springs here, and I think this is cool stuff, so get ready. When we have springs, now springs store energy as well. They are another form of potential energy, a lot like our gravitational potential energy. And we have Hooke's law. Hooke's law tells us about springs, and it tells us that a spring exerts a force that is directly proportional to its displacement. So that means the more I stretch a spring, or the more I compress a spring, the more force I'm going to get from it. That's what directly proportional means. As one increases, the other increases. And our equation for this is Fx, that's what we call the spring force here, is equal to negative k delta x. And notice I've drawn some vector arrows here. So Fx is equal to negative k delta x. The spring force is the negative of the displacement times this k value. And that k value is the spring constant, k, which is how powerful the spring is. And k has units of newtons per meter. And that makes sense. We're saying that for every meter of displacement, we're going to have a certain number of newtons of force. Good. We have a picture here, just below, of a spring and sort of the motion it can have. The first picture on the left says relaxed state, our force is equal to 0, and the block is at x equals 0. We call that equilibrium. This is equilibrium. Okay, this is our equilibrium. And then this second picture, you see we've stretched it. So x is positive. You can see that we've pulled it out, and the spring force here is pulling it back towards equilibrium. So the spring force is negative if x is positive. And our final picture here, we've compressed it so x is negative, and you can see that the spring force now is positive, again trying to pull it back towards the center point, the equilibrium. That's how springs work. They're always just trying to get back to their normal state. If you stretch it, it just wants to go back to normal. Good. So we have a problem here. It says a spring hangs at rest from a support. If you suspend a 0.46 kilogram mass from the spring, its deflection is 7.9 centimeters. And deflection, that's just another word for its displacement. Okay, that's how much it's stretched. We have a picture of it to the right. We want to first determine the spring constant. It says that the 0.46 kilogram mass is just hanging there. So it's at rest again. So we could draw a little picture for our mass, and we could say, well, it has the spring force, right? We have our Fx upwards, and we have mg downwards. So that means that in this case, Fx is equal to mg. Well, it's equal to negative mg. And we can go ahead and solve this now. So we're going to have our Fx, well, Fx is equal to, we said negative k delta x. So if we want to find the spring constant k, well, we have k is equal to, you can see it's going to be negative mg over negative delta x. So we get mg over delta x, and delta x should be a vector as well here. Good. And I can put in some values here. So my mass was 0.46. G is going to be 9.8. Down here, delta x, we have a deflection of 7.9 centimeters, so 0.079 in the same direction as G. And this gives us a value of 57.1 newtons per meter. And that's our K value. That is our spring constant. We found that by doing our free body diagram. Now the next step here, we want to calculate the displacement in centimeters of the same spring when a 0.75 kilogram mass hangs from it instead. So now we're going to have, again, equilibrium. And we're going to say that we have, again, our X force, our spring force, and down here we have mg. They're going to be balanced again. So we can say, again, negative k delta x, this is our X force. We'll say Fx is equal to this, and it's equal to negative mg. Okay, we want to find the displacement, so we'll rearrange for displacement. Delta x is equal to mg over k in this case. And we'll use our mass, 0.75, times g, 9.8, over k, which we found in the last one was 57.1. And this now gives us a value of 0.13 meters. We were told to say in centimeters, so it's 13 centimeters. There's our final answer. Now you might have noticed part A, I was trying to draw arrows. I quickly dropped that. In these spring problems, since we're always working forwards and backwards, it ends up being pretty easy just to leave off the arrows, leave off the vectors, and just talk in scalar terms. That's fine for now. Okay, part C. It says, suppose the 0.75 kilogram mass is pushed upwards so that it rises past the spring's unstretched position, and it's now compressing the spring. We want to calculate the net force on the mass when the spring is compressed 5.3 centimeters. And we're going to include a free body diagram. So that's what we'll draw first. We've got our free body diagram. We still have mg working downwards. And now we don't have a spring force upwards. We've compressed the spring, so now it's working downwards on us. This is our Fx. So we have two forces acting down, and we actually have to be holding it upwards. So maybe we have our applied force holding it upwards. You know what, I'm going to pretend that's not there. This problem is imagining that you've just released it, and we're going to see what the force is going to be. So this is our force now, and we want to calculate the net force. So we can say net force is equal to mg plus Fx, which is equal to mg. Remember, our Fx is equal to, well, negative k delta x. Okay, good. So we'll plug in some numbers now. So we have m is 0.75 times 9.8 minus k, which is, if I just look above here, is 57.1. And delta x, now before we were saying delta x downwards was positive, so if we're going up now, we've got to say it's a negative 5.3 centimeters. And really I should convert that 5.3 into meters. Negative 0.053 meters. Good. Okay, and we get this net force here. It should be equal to 10.4 newtons. And if I call this a vector, we can say that this is pointing downwards. Good. Now we want to determine the acceleration of the mass at the point given in C once it is released. Okay, so we have the point given in C. We're going to release it. And what's our acceleration? Well, we can say net force equals ma. A is equal to net force over m. And this is a pretty easy one. 10.4 newtons over our mass, which is 0.75. And that gives us 14 meters per second squared down. And there we go. That is our solution. So we'll check page number 2, where we're now talking about elastic potential energy. So that was our only problem like that. You'll have some problems, some homework problems that look like the same sort of thing. Okay, elastic potential energy. Now we're talking about the energy that's stored in this spring. So this is the potential energy due to stretching or compressing an elastic material. An elastic material. So we're talking about any elastic material here. Springs are the really obvious one, but really anything. You can have actual elastics, rubber bands. You can have trampolines. You can even have just some sort of, like a plank of wood is sort of elastic. It stretches. So really we can use this for a lot of things, but we're focusing on springs here because those are the easiest to understand. Okay, we have an equation for the energy, elastic, so EE is equal to 1/2 delta x squared. Okay, and I've put that delta x in brackets, so it's clear that we're squaring the delta x. Okay, and maybe that looks a bit like 1/2 mv squared. I don't know, it's a bit related. So we've got a problem here. A 42 kilogram teenager balances briefly on a pogo stick, causing the spring in the stick to compress downward by 0.18 meters. Determine the elastic potential energy of the teenager. Okay, so this teenager is balancing here. So again, the forces are going to be balanced, which means that we can draw a little free body diagram, and we can say that this teenager has mg force downwards, and that's going to be balanced here by our by our fx. If I'm drawing my free body diagram here, and I want to determine the elastic potential energy of the teenager. So first up, we need to figure out what our k value is. Okay, because actually no, we don't need to do that. Sorry, give me 1 second here. Okay, so this makes a lot more sense. I made a mistake above. I thought that didn't look quite right, and just in my haste, I wrote it down wrong. So 1/2 k delta x squared. That is the correct equation here. We need that k spring constant, and now you can see it does look a lot more like 1/2 mv squared. Okay, so we'll go back to our problem here. We've got our fx and our mg, so this means that fx is equal to mg. So we can say that our, let's see, we've got our k delta x, negative k delta x is equal to mg. So if I want to find k, it's going to equal to negative mg over delta x, and we'll just go ahead and plug in some numbers. So we've got g acting downwards. Our delta x is downwards. So we can cancel out some of these negatives and positives here. So we've got 42 kilograms times 9.8. Delta x is going to be 0.18, and we get a k value here of 2.29 times 10 to the 3 newtons per meter. Okay, there's our k value. Now we need to get our elastic energy, which is going to be 1/2 k delta x squared. We've got our k value, 2.29 times 10 to the 3, and delta x was 0.18. We'll square that. And this gives us an elastic energy of 37 joules. That's our elastic potential energy. And there we go. That's how we can find that sort of a value. Okay, Before we move down, I actually want to move back up for a second and take a look at the picture that we skipped over on the right here. This picture here. Okay, so let's take a look at that picture, and what I would like to say is that you can see this is our force versus x. And remember, we have F is equal to negative k delta x. And so you can see what's happening here. We have our slope is negative k. That's our slope. So you see we have a straight line. And so that's what's going on here. And if we take the area under that curve, we get 1/2 F delta x. And that is how we derived our equation for the energy. That is the work that's being done here. So you can see that the area under the triangle, that's F times the distance, which is equal to our work done. Okay, good. So we'll just pop down to the bottom of this page here, talk about this idea of simple harmonic motion. So simple harmonic motion is periodic, which means back and forth motion in which acceleration is proportional to displacement. Acceleration, oops, I spelled that wrong, is proportional to displacement. Perfect. And so we're talking about our springs here. If we have a spring, let's say a mass attached to a spring sitting on a table. Okay, imagine it's horizontal. And the spring is attached to something on one end and it's attached to a mass on the other end. If I pull the mass out and let it go, it's going to bounce back and it's going to oscillate back and forth around the equilibrium. And if there was no friction at all, if this was on ice or something like that, then it's going to keep on going back and forth about that equilibrium point. And that's what we call simple harmonic motion. Now, it's neat to look at simple harmonic motion for springs, and one interesting thing to look at is the period of that simple harmonic motion. And we can actually, for any given spring, we can say what the period is going to be. The period of that spring will be 2 pi times the square root of m over k. And your textbook has a long derivation that shows how that was actually found. We're not going to go into that, but it is interesting. Okay. And it has units, of course, of seconds for a period. So this is how long a single cycle takes for it to go from its max to its min and back to its maximum again. So we'll see one problem here. It says, suppose a diver of mass 85 kilograms stands on a diving board with spring constant 8.1 times 10 to the 3 newtons per meter. We want to calculate the period and frequency at which the board vibrates. Assume the board is light. By that I mean just that it has no weight. We can ignore the weight of the diving board here. Okay, so what do we want to do? We want to find the period and the frequency. So we'll start with our equation for period. 2 pi square root m over k. We know the mass of the person. That's what m is, the mass of the person. And we know the spring constant. So we have 2 pi square root 85 over 8.1 times 10 to the 3. And it's nice and easy when we're given the spring constant. Very little work that we have to do. So we just plug in those numbers and we can find the period is 0.64 seconds. Now we use our relationship t is 1 over f. The period is 1 over the frequency, or if I want to do frequency, it's 1 over the period. So it's going to be 1 over 0.64 seconds. And this gives me a frequency of 1.6 hertz. And you can see that if we're given the spring constant here, that becomes very easy. It can be a trickier problem if we need to find out the spring constant, just like some of the problems we saw earlier. Great, that's the end of the lesson. I'm sorry about the hiccup in the middle there. I really am. I made a bit of a mistake. So thank you for listening. Enjoy the homework.